Or is that little record sign not going to pop up? Normally it pops up pretty quickly. There it goes. Welcome to the APAC community call. Today is June 3rd, 2021. So we have quite a full schedule here as well. So first I will bring over some news from OHDSI, and there's some excitement from the OHDSI side that I want to talk to you guys about. And then we have two presenters. We're honored here to have Professor Kang, who's going to talk to us about automating terminology mappings via deep learning-based semantic matching. And then also I see Ty, Dr. Ty is here, Ty Sanford is here, who will be talking to us about Legend. And my guess is this is the Legend type 2 diabetes one, right? The newer Legend project, or is it the?
It's about the online Shiny app.
Okay, cool, perfect. So just a little background here. Professor Kang is from the State University of New York, Korea. And you can read here a little bit about where he's been, but quite a few places, including Aju and Samsung, before landing where he currently is now at sunny Korea, as well as Dr. Tai here, who is with the University of South Australia. And I know he's been in OHDSI for quite a while now. So before we go to their presentations, I do want to bring up the news of OHDSI. Oh, I had it up and I guess I must have closed it. So what has been going on in the global OHDSI in the last 2 weeks, right? Again, to get to that, you can just go to this OHDSI community call and you can read more about what's going on. So this week, what's really interesting is they actually did a mid-year review of the OHDSI Global OKRs, which is basically OHDSI Global's overall goal for the year. Patrick and folks presented on it. You can see the slides here as well as the actual whole presentation that you have here. The reason why I was asking Ty was what were you talking about, because one of the things that if you go to the OHDSI chat that they were talking about that Mark actually brought up was a type 2 diabetes Legend project that they're starting. You kind of have to go up this thread to find it because they were talking about. So here, Legend type 2 diabetes needs support in many ways. So they're kicking that off. If you guys have an interest in it, I would suggest you reach out to Mark and folks to better understand what they're looking for. But the other thing that they actually talked about is one of the goals in OHDSI is to study different research areas, three different research areas. One was COVID. I can't remember what the second one was, but the third one is health inequality. And from all of that, what we just upon talking about it, and again, if you go to the community, OHDSI community page, you'll see all this chat in there. But they do talk about a lot of the interest of health inequality. And what Patrick has suggested is actually starting a working group. Where did he say that? Starting a working group on that. So if you guys have an interest, you can actually look out for that working group. So here they're going to start a health inequality working group to talk about, researching diseases, certain different inequality in diseases. So again, if you're very interested in any of these topics, come to this Teams chat here where the community call is, as well as watch the video that you see here, which Patrick went through about all the different OKRs that they're talking about. Like one of their accomplishments up to now is they've done more than 10 publications that has an impact factor higher than 10 thus far already, and there's a bunch of them that's still in the books, right? So for example, there was one that came out this week here, this particular one using the CRIBDIS study that was just posted in the pediatrics. And then, last week there was another one, I believe from the Korean side, where this was published in BMC Medical Informatics and Decision Making. So lots of publications going out there, lots of stuff happening. The two other things that I want to bring to your attention is this next CBER Best Initiative. And if you guys don't know what the CBER Best Initiative is OHDSI won the project to work for FDA on vaccine surveillance for COVID-19. So they have a series of talks about how to do that, as well as education and project coordination stuff. So their next edition of this is actually going to be on June 16th at 11 a.m. Eastern Standard Time. If you guys are still awake at that time and want to actually register because it's free, you can click on the link here. The other thing I do want everyone to be aware of is the symposium abstracts. They are due within 3 weeks. So there is less than 3 weeks left to actually submit your abstracts to the Global Symposium, which is taking place in September. If you guys want to know more information, you can click on these links here. It'll take you to the showcase page, show you what the format is to fill everything out. If you have any questions, feel free to ask the community, or you can ask me. I'm on that committee, on the scientific committee for the abstracts. So where necessary, I can help answer some questions for you guys as well. So those are at a very high level, the updates from OHDSI in the last 2 weeks. Anybody got any questions before I turn it over to Professor Kang? Nope. All righty. I will stop sharing. And Professor Kang, do you want to share your own screen? Oh, we can't hear you. You're on mute. There we go.
Can you hear me now?
Yes.
Okay,
perfect.
Great. I'll take over the screen then.
Thank you.
This is my first time using Microsoft Teams.
It's the little box with an arrow on top right next to the
I see.
button.
There it is.
Yeah, and it might make you pick certain ones to share.
Mm-hmm.
Okay.
Got it.
Yeah, it's coming.
All right.
There we go. Yes.
So do you have the screen? Okay.
Yep.
Let's see if I can do this. All right. So, oops, sorry. I don't know why this is happening, but it's just. All right. So I'm very pleased to meet all of you. I'm honored to be at this place. I'm sorry. This is just flipping on its own. Let me just take care of this slide transition.
It's okay. Teams is funny.
Would it be okay if I just showed you this screen instead of the full one?
Yeah, that's fine.
All right. Well, sorry about that.
Well, you're not sharing right now anymore, so you stopped sharing.
Oh, my bad. My bad. Okay.
It's coming. Yes.
Okay.
Now we see your presentation.
Okay. So, yeah, I'll just proceed like this.
That's fine.
So, okay, thank you. Nice to meet you all. My name is Byung. I'm actually one of the authors of this paper about the topic I'm about to present. And what I'm going to talk about to you guys is about how we can use deep learning-based technologies, in fact, representation learning-based technologies to perform terminology mapping to a standard set. This is, of course, a joint work with all of my colleagues presented here. I just happen to be the one who had time at this moment. So I'm certainly not the best expert to give you talk on anything done at OHDSI, but hopefully I can give you some idea about some of the machine learning based works that we did on it. Okay. So by the way, do I have 20 minutes to present?
Yep.
Got it. Okay. All right. So I was approached with this problem with a very practical motivation, and it's about records being maintained at multiple medical institutions, mostly hospitals. And as you can all see, hospitals usually contain a lot of records about patients, the devices they possess, all the treatments they've done before, etc. And it's going to be very important to somehow systematically manage all those records. And one way to do it is to assign something called a code or a term for each document so as to classify them into an appropriate class. Okay. Now that itself will provide some kind of systematic control or systematic management of the documents, at least locally. But then the problem comes when you have to compare or merge two sets of records from different institutions. Because apparently it's not guaranteed for the institutions to have the same code set or the term set, as we say it. So if we want to make some kind of analysis, inter-institutional analysis among the records, then there has to be some kind of way to sort of standardize these terms. So the most obvious solution that we can think of is to come up with a global term set that everyone can agree with, and then perform a mapping of the individual institutions' code set to that global standard. And apparently this is one of the efforts being done by at OHDSI. So the problem we want to solve becomes a little more specific then. So, and the input to this problem is actually a candidate term from a individual institution. And what we want to do is we want to produce a mapping from that term to a standard set that has the same semantic meaning. So at first glance, it might seem like an impossible task, because if we're just given the tags, or sorry, if we're just given the codes, then we don't have any contextual information to map one tag to another one. Right? So, bluntly put, how can we measure the similarity between the code A390 to 56-C? So if we just look at the tags, it doesn't really make sense. So we need some more context to do semantic level mapping. And fortunately, practically most institutions contain their own standardized terms. For example, many hospitals in Korea use the SNOMED CT, which fortunately again they contain terms that are paired with the corresponding description text of each term. And even if we are not using SNOMED CT, it's very reasonable to assume that each code will come with a corresponding or in some appropriate form of this description of that code, because otherwise it would be very difficult to manage all those tags. So in this work, we're going to assume that these individual institutions' codes are paired with the corresponding description text. So now the basic idea of our approach becomes a lot easier. Now, since each term will have a corresponding description text, and we're also assuming, well, I mean, we all know that the OMOP CDM contains all the term set with the corresponding description text as well. So we can use that description text to extract out contextual information. In other words, we can try to map one code to another code that has a similar description in terms of semantics. And it turns out that this approach is not really completely novel, because apparently Usagi does something pretty similar. We don't know the exact algorithm of Usagi, but the overall idea is to perform some kind of word count or word statistics-based semantic matching. More specifically speaking, it'd be term frequency and inverse document frequency-based matching, if I remember correctly. But of course, that is really just we can certainly do better than that, because if we want to accommodate more, deep semantic of the description text, then we should probably look a little deeper than simple word counts. So, of course, I don't mean to discredit Usagi, but I'm just proposing a way to take another level into the semantic area. So one way to deal with this is what the machine learning people call representation learning. And it's another one of those big words adopted by AI people. And it's really nothing more than a set of techniques that allow you to represent any given object into some kind of number, or quantify the meaning of an object. And in most cases, we aim to represent a given object as a Euclidean vector. And this is also commonly known as embedding. Now, I know many of you here will probably be very familiar and actually have quite a level of expertise in machine learning, but I'm just going to assume that some of you are relatively new to this area. So let me just explain a little bit about what embedding is in a nutshell. So the basic idea of our approach is to represent the description text into a semantically meaningful Euclidean vector. So in other words, we want to embed these description texts. And there are a couple of many well-known algorithms that can do that. Skip thought, %, BERT is also gaining a lot of popularity nowadays. But of course, even if we do manage to embed these description texts, there's still a problem of how to decide if two embeddings are similar. So that issue is the learning part. We're going to address that issue by proposing a neural network architecture that can perform similarity computation. A little more explanation about embedding is that basically you want to represent the objects as vectors such that similar items will be represented as vectors that are nearby, and different items will be represented as vectors that are far apart. So that's the nice thing about having vectors. It's because if you have vectors, it's a little bit of a math lecture, but if you have vectors, it's pretty easy to measure a raw level of similarity by using what is known as a dot product or an inner product. And also, if you have a vector, then you can also measure distances. So that means you have a way to somehow compute a very simple form of dissimilarity as well. And based on those operations, you can perform many different analysis tasks, like clustering, which is grouping similar items together and separating out different items. You can also perform classification. So that's the benefit of representing items or any kind of object as a vector. So it's basically the fundamental step in all or most modern machine learning algorithms. So again, just to reiterate our main approach, we would like to take the individual description text and represent them as separate vectors that contain quantified semantics. And then we want to find a way to measure the similarity between any given two pair of such vectors. And that is done by our proposed neural network architecture. It looks a bit complicated, but the actual training part is only this portion here. So let me just explain briefly what this does. So this will take two different inputs. The first one would be the source code description, which is that the description of the code that you want to map to the standard set. And on the other end of the input, you also give the description of the candidate mapping part. So in goes two different description texts, and you can perform embedding by using any of the embedding algorithms out there. In this case, we used InfraCent to produce two vectors, corresponding vectors. And based on those two vectors, we form another intermediary vector by performing a series of relevant operations. And that is going to be the input to another neural network, which I draw as a red box. It's actually a series of fully connected layers in case you're interested, but it's a relatively simple portion of the entire model. And given that, this red box will output a single number between 0 and 1, and that's going to indicate the probability that these two input should be a match or not. So if it's closer to 1, then it should be a matching. If it's closer to 0, and it's probably not a correct matching. At least that's what we intend it to be in the ideal case. And in order to train this whole thing, or actually this thing right here, we want to increase the probability of the correct match and also penalize the incorrect matches as well. So we call this architecture Toki, which is a backronym meaning rabbit in Korean. And once you finish the training of that component, you can just run, you can use that architecture to perform the actual matching during test time. Okay. So in this case, the input would be the source term that you want to match to. And once you're given the source term, you will simply have to go through the entire descriptions of the OMUP CDM. And for each description corresponding to each term in that OMUP CDM, you will simply compute the similarity, the pairwise similarity between those, and simply present the 100 most similar matches. And of course, this similarity term here is computed by our proposed network, so it's a well-defined one. And notice how I originally talked about finding the correct match, and instead here I'm suggesting that we should present the we should present the 100 most similar items. So trying to find a single matching candidate would seem like a convenient way to solve this problem, but instead it does result in a lot of false positives. And instead, as a practical compromise, we found that it'd be much more efficient to present the top 100 most similar items and have the human operator sort of filter out the false positive, including the top 100 results. And so this one is something that we learned from the actual operators, that their jobs would become significantly easier if one good matching was to be included in the top 100 results. So our training set is actually another important observation that we made during this research. And the performance of our system varies depending on the way we present and prepare the training set. So the training set is usually given like so. So a single instance of a training set is actually composed of 3 different components. The first one would be the source term and description pair. The second component is a target term and description pair. And finally, the last component is the label itself. It's a binary label indicating whether these two should be a correct match or not. So obviously, the positive samples where these two are being a correct match indicates that these two samples should be sort of brought together, whereas a negative sample should act as a repulsive operation where mismatches should be separated out. And as we'll get to see in the actual experiment results, we learned that we need a lot more negative samples than positive samples, and we'll talk more about that after the result presentation. And the way we should collect these negative samples, where y equals 0, is also quite important. And we present 3 different schemes to collect these negative samples. The first one is perhaps the most simple one, known as the random sampling scheme. And this one is really just an intuitive approach where we just come up with an arbitrary description chosen at random from the given list and match it with the given concept name. And that would create a mismatch, definitely, most likely. So it's very easy to create random samples, very easy to create random negative samples. So this one is the dominant portion of the entire negative samples. Another scheme is what we call the false positive sampling scheme. And this one is actually based on the feedback from a pre-trained model. So we come up with a very rudimentary form of the mapping model, maybe a model that we trained during the earlier iteration of the training phase. And based on that, we can compute an intermediary similarity score, or some kind of intermediary mapping result. And if we ever find false positive samples in the top 100 list, so if we find something that should not be in a good should not be a good matching in the top 100 list, then we take that to be a negative sample. So we're essentially taking a feedback from a partially trained model and insert it back into the negative sample list. Last one is somewhat specific to certain data set, and we call this the hierarchical sampling scheme because we're taking advantage of the hierarchical nature of the term set. And the reason why we thought about this was mostly due to the way SNOMED CT is structured. And here the clinical terms are given in a hierarchical structure, where certain terms have higher location up in the hierarchy, meaning that they're more general, and some are more specific. And it turns out that many of these terms that belong to the same hierarchy lineage tend to get confused a lot, and we don't want them to be included in the top result. So what we did is we just chose once we located the ground truth matching term, we moved up or down 2 levels in both directions and chose those terms as the negative samples to indicate that they shouldn't be inside of the top 100 list. So this one is more specific to the term set that has a hierarchical nature. And using all those actually produced the best result. So this is a quantitative result of all the configurations that we had, and we have the result from Usagi on the leftmost column, the result. And the first column contains all the various criterion, and the second column is a result from Usagi. And the remaining ones indicate our differing configurations of the training set we produced, starting from the random samples. Here we have this notation, some number n followed by the word POS, and that indicates that we used the random negative samples where there are n times more negative samples than positive samples. So 50 POS means that 50 to 1 ratio of negative to positive samples. And in addition to that, we also incorporated the false positive negative samples. And finally, throwing in the hierarchical negative samples also resulted in some additional boost towards the end. So this final configuration consistently performed better than the other approaches. So this is our final proposed approach. And we can take a look at some of the qualitative results. By the way, this one, I believe it wasn't cherry-picked, but in our paper, there's also an instance where Usagi performed better. So I think I forgot to bring that up. It wasn't intentional, by the way.
Oh, no, don't worry. It's okay. This is quite interesting.
But yeah, I meant to actually show you what our model can do. But anyway, you can see that in this qualitative result, this is the correct matching description. And the ones you see on the two right-hand side, 2 right columns, are the top 10 results of the individual algorithms. So rank number 3 contains an actual match to the true match, contains an actual match. And you can see that it consists of almost no overlapping. Oh, actually, there is lumbar here, spinal as well. But this one, the one that we found, is much shorter than the original source description. So you can see that simple word count based approaches would fail to identify this particular case. So this is one advantage of using a semantic-based matching. And just to give you a little overview on the one that I actually omitted, is where Usagi did better than us, is when an actual word-to-word mapping performed much better. And those are some of the more often used cases. So, which is why we're not claiming that Toki is a strict replacement of Usagi. Rather, we should actually be a complementary system. So maybe we can come up with a system that can perform the same task by combining the results of the two systems. Although that's left as a future work in case you're interested.
I was just thinking about that.
Also, let me just talk to you about the negative samples. So apparently we do need a lot more negative samples than positive samples. Although 1 to 50 ratio is suffice to bring up yield good enough results, but mostly because there are only a very limited number of positive matches, and you actually need a much stronger repulsion force to push away those negative matches. And I was actually quite surprised that we only needed 50 in terms of the ratio. I was expecting the order of at least 100 or 200 maybe. But maybe this was just a small case. But in general, you do need a lot of negative samples to come up with a good similarity matching system. So in case you want to try this out with some other data set, then maybe you should consider fine-tuning that number. So that is what I have for today. Hope I'm not too late, but are there any questions?
I find it very interesting. So like you mentioned earlier, I would love to see if there's an interest in the community at looking at Toki and Usagi together, because then it gives us, like you said, a better chance, right, of matching these terminologies. So what you guys done it's very interesting, and I don't know enough about Usagi to know what it does under the hood, but that's something that maybe I can take back to the vocabulary team to talk to them and see if they have an interest, right, to maybe get with you guys to talk about what they do, and you guys can talk about what you've done, right, and maybe as a future project, get them Usagi V2.
That sounds great. Right. I mean, we originally intended our final part of this project to be a combined system of Usagi and Toki. We just couldn't find this right source code for Usagi, and plus we didn't find it would be appropriate to, manually modify the source code, even if we had access to it. So maybe if you can, bring the experts, then we can talk about this approach.
Yep, I will actually talk to the vocabulary team.
Thank you.
Luckily, the owner of the vocabulary team is my manager, so I can talk to him directly. So cool. Well, thank you very much. Does anyone else have any questions for Professor Kang?
I do, if that's okay. Super interesting work. Thank you so much for presenting. And I wish you had more time to hear more details. I was wondering what form might you make it available to the OHDSI community, because I'd be very interested to try it on our vocabularies. Would you provide the multi-layered network machine learning system as trained by your
definitely
training samples, or would you want others to add to the training as well and other type things?
I think we can do both. We'll have to contact the actual student who managed all the source code, but we can definitely release this on GitHub so that everyone can access the source code. We will also release the trained model so that hopefully you can reproduce the results that we presented in this paper. So whichever approach that you prefer, we will try to help you out.
No, that sounds great. GitHub and a way to test that it's working the way it should is perfect. It's really cool.
I love that idea, Ty. I would love to try it too, because I've got lots of data to try this algorithm on.
Great.
Yeah.
We'll have it up online as soon as possible. I don't know why they didn't do it in the first place.
That's okay. No, that's okay. I'll have the OHDSI folks, the APAC OHDSI folks, reach out to you guys to coordinate that. And when you guys have it up, then we can put it out there and tell folks where it is. So.
Okay. Could you also, like, if you ever contact us, could you also send an email to our corresponding author, Dr. Kang?
Yep.
Yeah, thanks.
Anything. Any other question that anyone else has? If not, Ty, you're up.
Thank you.
Thank you.
So how do I disable the sharing?
Oh, you just do the stop presenting. So there should be at the top a button that has an X.
Hold on.
If you hover over it, it'll say stop presenting.
Oh, okay. Hold on.
Yeah. Technically, Ty can still just steal the presentation.
Do you want me to do that?
Yeah, you don't need to wait for it. If he takes it, then you get disconnected automatically.
Okay.